got our little, you know, little pause there. Before we start, I want to just say that we're having an intern panel this Friday at what time, Lazaro? You know what time? You know what time it is? Presume at 5 p.m. earliest. Um, yeah, we're just gonna talk about how we were able to secure something and sort of tips and tricks we could that we know and we've been collecting over the years of how yeah, you can get an internship. And some of us have had internships, and you can get to ask them how it was and like what the process was. So I do recommend that this Friday you do turn up, or at least perhaps watch the live stream. So look out for that. I think it'll do you all a great service to um, will help you advance in your career. Yeah. Are you going to be there, sir? You know what? Yes, I am actually going to be there.
Are you going to be speaking?
I am going to be speaking. Yeah. Thank you. Thank you. Thank you. You know, just wanted to give some people some advice that I learned that I will tell you at the event, but not today. So today we're going over single source shortest path problems on LeetCode. And let me actually pull it up right here. Okay. So what does that mean? I mean, just listening to the name of it, single source shortest path. What does that make you think? Like what is that? What stands out? You know,
Can you say it again?
single source shortest path.
Shortest path it takes to get to every node from a single source.
Right. That's a graph. That's a graph algorithm, right? So from one node, you want to get the shortest path to every other node, right? And that's it. And you tabulate that, and you can then have a whole record showing, oh, what's the shortest path from here to there. So that's what we're gonna do. So let's start off. We're gonna do this problem called network delay time. You are given a network of n nodes labeled from 1 to n, and you're given the times, which is a list of travel times directed by times I equals ui, vi, wi. ui is a source node, vi is a target node, and wi is the time it takes to get from the source to the target. So we will send a signal from a given k node. So k is going to be a number from 1 to n, right? And you want to find out from k, how long does it take, how much time does it take for all n nodes to receive the signal. If it's impossible for all the n nodes to receive that signal, return -1. Okay? So here, for instance, let's say our k is 2, so our source is 2. And we want to know how long does it take to get to every node, the signal. So this one takes 1, this one takes 1 here, this one takes another 1. Just looking at it, it's what? How long does it take to get all nodes from 2? Yeah. And why is that? So 2. And 4 is the longest one, right? So really, what this is asking you is how long does it take to get to the longest one? That's the question that you're being asked. So, yeah, that's pretty much all they're really asking you. And if it's impossible to get to all of them, -1. All right? Okay. So, now, we're going to go over, well, the actual problem that we have to solve. Before we start, I'm going to import some libraries. Import keepq as HQ and import elections. I mean, I don't need to do this part, but I just did it just in case. So we want to create an adjacency list to start off, right? And why am I creating an adjacency list? You want to say it?
To represent the graph.
Yeah, we want to represent the graph because the way it's given to us is just a 2D matrix, right? Or a list of 3 tuples, triples. a list of triples, where the first number is the source, second number is the destination, the third number is the weight. So that's the amount of time it gets to get from the source node to the target node. So we're gonna go through the actual input array. So I'm gonna say for t in times, or do you want me to put time? Does that make more sense? Or maybe, what do you think? T or time? Do t. So for each t in times, right? Right. T is a triple, right? So we want to say that the first source node, right? We want to store that. So we say add list, right? So we say t 0, because that's the source, dot append. So why am I putting append? Why am I putting append? You're getting it. What are we appending to? Well, it's a dictionary, but we're not appending to the dictionary. Remember, what is a dictionary? What is a hash map?
It has two values for
Okay, which are the
reference values,
the keys.
keys, and then the actual values.
Right, yes. So what is the key? Well, the key could be anything, but the values I specified. What did I specify the values to be? And for add list here, a list. So that's why I'm appending to this. Even though it hasn't been set up, it is an empty list by default. So this key, which is the source node, what do I append to it? What should I append to it? Well, what are we going through? What in this for t in times? What does that mean? What is t? Actually, you know what? We could actually decouple this. There. Kind of like what we have right here. Okay. So the key is the source node. What the list is a list of what? For that key. Since it's an adjacency list, it's a list of the adjacent nodes, right? So what do we put here? What do we have to append? The target node, right? And what else? Yeah, which is the weight. W. Yeah, perfect. So that's what we have to do, right? We append all those into a list, right? We're representing the graph this way. So now I am going to make a min heap. Well, get to that. I'll make a dictionary of a distance. It's going to be a table, right? And what do you think? What do you think it is? Okay, so what did we say K was? What did we say K was?
K is the current node that we're starting off.
Yeah, so that's our root node. That is where we're sending the signal from. Okay, so we say that the distance to K is 0. I mean, it's itself, right? Yeah.
Also, we're gonna find the distances from A to every node in the list.
Yeah. So what's the min heap?
The min heap is the,
Well, it's not
well,
empty.
it's not empty.
Yeah.
So is it going to go through every node in the
Actually, let's not do this one. Let's not do it like this. Let's make it 0 at first. And we'll see why. It's gonna go through every node. How? Como, sir? Como?
so the left is the distance it's currently on, right? For the min heap.
Yeah, so 0. And then the right is, well, the value of the node you're on. The one you choose. What is a min heap?
A tuple.
No. I mean, those are the values I'm putting in the min heap, but what does the min heap do?
It stores the distance
No, I
from.
mean, in general, if you had a min heap of numbers,
I don't know what a min heap is.
okay, a min heap, right, is a priority queue. Maybe if I say priority queue, does that make sense? All right, so you want to be able to insert based off of a value, right? And let's say you want to search based off of a minimal value. And let's say you got 0, 2, 3, 4, 8. See, I have that. Okay. So let's say I want to remove a value, but I want it to be logarithmic. Like when I remove it, the runtime is logarithmic and not linear. I want a sublinear remove, say from a list, right? That's what I want to do. Okay, let's say I remove a value from an array. What's the runtime?
You have to make the whole array.
Yeah, exactly. And that's linear. What if you didn't have to do the whole thing? What if you had a procedure where it could be sublinear? It could be logarithmic. That is what a priority queue does. Particularly, this is a min heap. So see, the smallest value is always at the top. So searching for the smallest value takes O of 1, constant runtime. Removing it will rearrange the values in some way, but that rearranging is log, not O of n. Yeah.
Can I add to that?
Yeah. Yeah.
Even when I'm hearing it, I'm a little confused.
Yeah.
But a min heap is a data structure, right? And it's very simple. You can ignore everything else, the inner workings of it, but you have some data structure that keeps numbers. You can add numbers in some logarithmic time. It's not constant. And then you can only take out the minimum value in
Yeah.
logarithmic time. So it's very simple. You're putting in numbers and then always taking out the minimum. And it does everything else. It works like a black box.
Also, always take out the minimum.
Yeah,
So like
that's its goal.
Yeah.
So like from there, if he keeps taking out, go 2, 3, 4, and then it'll take out 5 and skip over 8.
No, because here's the thing. The smallest will always show up here. And not only that, well, think about it as a tree, right? A binary tree. Like, okay, I don't want to get too much into it because it is complicated, but they treat the indexes as nodes in the tree, right? And its children are, the left child is the parent times 2 minus 1, and the right child is just times 2. And it's the same thing. So the children for this one are these two, right? Okay. All that matters is that the parent node is smaller than the children. That's it. That's all it cares about. And then it's going to rearrange it in a tree-like fashion, a binary tree-like fashion, and it's done in logarithmic time. We don't have to get too much into why it works, but it's a fast way of storing our values. and taking them out and putting it back in. So why are we using this at all? Why are we using a min heap and comparing it? And basically the comparison is actually the distance. We're going to order it by distance. Okay. So why am I doing it by distance? To get the smallest distance when I pop it. Why am I doing that? Yes, you want to start with the smallest one, right? You want to start with the smallest one because maybe from there you can get the smallest one to the end. So that's pretty much it. That's why I'm using a min heap. So I'm going to get the current distance and the current node, and I'm going to get it because I'm going to pop from the heap. There it is. Min heap. Right. So I'm going to check that if cur dist, so if I already calculated the minimum distance to the node we're on right now, that means we already found the minimum distance. Now, that might sound confusing. I'll answer your question soon, but you only need to calculate that current distance to that node once, and that's it. It's already minimized. Please ask questions if that sounds confusing. Okay. So if it's in there, continue. But if it's not in there, then I'm going to set the current node's distance to the source as this distance we calculate. So let's say current node is k, the source is 0. Exactly. So now where do we go from here? Where should we go from here? Bless you. Okay. Where do we go from here? So we did the current node. What do we do? Traverse the nodes adjacent to it, right? So for edge in list, edge list, and it's gonna be of what? It's gonna be current node, right? Now also we know that it's just v and w, right? So I'm actually gonna make it. I could make it v and w again. Yeah, I'm gonna make it v and w if that works. I'm gonna decouple it. So v is the node we want to go to. So we want to actually, all we want to do is just push to the heap. And what runtime do you think heap push is gonna be? Yeah. And what did we say we wanted to do to make it sublinear? So it's gonna do it in log time to push to the heap. Yeah, it'll rearrange it in some way, but it'll be sublinear. So that's the focus, so that we don't have n squared. At best, we have an n log n solution. Not quite, but we'll see. So what do we want to push, right? We want to push the min heap, a tuple of what? So we just have to focus on what we did here, right? So this is what? This is the node, right? The second one is the node. Here was k. The tuple of things we want to add, like here. So we want to. So the tuple, we take inspiration from the first one we did, which was distance 0 and node k for the first one. Now I want to add to current node, right? So, well, the second is the node itself, right? The adjacent node. But now, yes, we want to add current distance plus what? Could be 2, could be 3, could be 4. But see, we have that information of what it is, don't we? Oh, yeah, you're right. We have W. So there we go. So for this one, in the min heap, we want to say that for this node, the distance is the current distance we are with the current node plus the amount of time it gets from that current node to V, which is W, right? Okay. Now what do we want to return, right? We're going to return -1 if the length of the distance is less than n, or it's not equal to n. Exactly. If it doesn't, that means we didn't reach all of them. So the distance dictionary is not going to have all the nodes as keys. But if we do, right, I'm going to get the max. So I'm going to get the max distance. So I'm going to make a what is it? This comprehension. Okay. Does this part make sense? All right. So let's explain this a little bit. So from this items, right, we want to get the max distance. So for each node and distance pair in the dictionary, right, I say, let's just select the distance, right? So we only have the list of distances, then return the max value. So this works. Oh, okay. No, it does not work because I put that, yeah. If of and not if. Oops. Okay, wrong. Okay, why is it wrong? No, it's -1 if length is not equal to n. Yeah. Else. Turn -1. Is there like a dictionary value? Oh, there is. All right. Okay, so there's a problem with our algorithm. It's returning -1 and it has an answer. What do you think, lads?
Can you slow down on the left side? Bro.
Oh, that's why.
Um,
There we go. Has to be node. If we haven't done the node, then yeah. If we haven't done the node, sorry guys. You know, sometimes it's like debugging, right? Debugging is just like, just gotta catch on to it and read carefully. So if the current node is in the distance, like we already, calculated its distance, and don't do anything else with that node. Otherwise, put that in the distance table of key and value pairs, and then go through all the adjacent nodes adjacent to current node, which is V and W. Okay. All right. So now this algorithm we just did. Anyway, the algorithm we just did, we used Dijkstra's. Yeah, we just used Dijkstra's right now. Mm-hmm. Is that like a charger for your phone and your watch? Yeah, I know he did. It was fine. I was just curious. Okay. problem is network delay time. And we use Dijkstra to solve it. The goal is to just find how long it takes to get from the source node to the longest, well, to all of them, yeah, but to specifically, they're asking the longest one, the max distance. That's pretty much what they're asking you to do, and that's what we did. Does that make sense? Just looking at it. Yeah, yeah. Yeah, exactly. Yeah, that's just what I do right here. In the values of the dictionary distance, I just get the max. Yeah. Also, there's this case where if you didn't go through all of them, that means it's impossible to get to all of them. If it's impossible to get to all of the nodes, that means the length of the distance is not equal to n, because there's n nodes. Then return -1, saying that. Yeah, it's a whole connected component, or it's two. Yeah. Okay, this was you solving Dijkstra. Now we're going to go through another problem, and we're going to use Bellman-Ford for this one. All right, this one's a little bit different. We're going to find out the cheapest flights within K stops. There are n cities connected by some number of flights, and you are given an array of flights where flights I represents the from city, the to city, and the price at the ith value. And it indicates that there is a flight from the city from to city to with a cost price. You are given 3 integers: source, destination, and k. Return the cheapest price from source to DST with at most k stops, and if there is no such route, return -1. Okay? So let's kind of look at this one. So here they say that the source is 0, the destination is 3, and the k equals 1. So with at most one stop in between the flight, what is the minimum, what is the cheapest price from 0 to 3 where you can have at most one flight in between? Like you have to stop once before you get to 3. What is it? Okay, it's 700? Yeah. And why is it 700? What if k was 0? Yeah, because you cannot get, you need to get to 1 or 2 to get to 3, from 0 to get to 3. All right. Yeah, to find the cheapest price from source, say 0 to destination, within k stops. Yeah, that is the goal. Okay. So, what we could do, right here. So I'm going to use this constraint right here. So I'm going to have a list of prices. And I'm going to make it 10 to the, they say the max price is 10 to the 4. So I'm going to say 10 to the 4 plus 1 for in range, say n. Well, no, because it's just one value. It's just this number n times. And what's the price to the source? Should be easy. How much does it cost to get to the source from the source? Yeah, exactly. You don't need to fly at all, so it's price 0. Okay. So, really quick, I think I'm missing a part. No, I'm not missing a part. So, before we continue, who kind of has a general understanding of what, like, how it works, Bellman-Ford? What the point of Bellman-Ford is. Now, of course, it is Bellman-Ford, but we don't need to check for negative cycles. There are no negative prices. Prices goes from 1 to 10 to the 4, so they're all positive. So we don't need to check for that. Negative weighted cycles. Is useful for this problem. Yeah. But you need to specify how many stops in between. Yeah, exactly. Mm-hmm. Mm-hmm. Exactly. Exactly. Mm-hmm. So before I go further, let's say this has like some path, and these are nodes, blah 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 blah, and these all go to the same node, and this node goes to other nodes, blah blah. All right. So let's say uh, at first we calculate that. Let's say stop. So the shortest path to this from one stop is infinity. This one is 6, infinity, right? And I said stop is 1, so that means we already went through. This is not the source, so let's say source is over there. Actually, this doesn't matter. This could be infinity. But let's say we up the number of stops, right? And maybe this stays the same, maybe it stays the same, but see, this was calculated. So now we can change this. Actually, I didn't put a weight. 3, 2, 5. Okay, those are the weights. So since the number of stops went up, right, I can actually change this because this was updated, right? And it's gonna be those two added together, 9. Now let's say we can keep going further, right? And then I change this, and this is 2. Maybe I update this one as well. Like maybe this becomes, I don't know, 5. And this doesn't change. So then what does this become? Yeah. That becomes 4. That's the idea, right? You may find optimal solutions in the past for other, subsequent, like previous cities, and say if you updated them and it affects this answer directly, then do it. So let's kind of go over. Let me use this arm. That arm is tired. Let's go over this problem actually. This one right here. 0, 1, 2, and 3. So we say their source equals 0, right? 3, 0, 1, 2, 3. And this is the price table. And, well, this 0 obviously is in, right? And we say that right now we're at stop 0, and we want to stop at k plus 1. At k plus 1, we don't do it anymore. Or we say that k is the max we go to. Okay. So let's say we're at stop 0, right? And let's say, we didn't say what the weight, well, they say right there. So if with 0 stops in between, right, how do we change 1? Okay, we do. So we change 1 and it becomes what? It becomes 100. Okay. All right. Then do we change 2? Okay. here's the tricky part, right? Every time you're going to update the table, keep a copy of it, of the previous values. That's just what you have to do. You're gonna have to do that, right? So 2, right? 1 goes to 2. In fact, it's the only one. And originally it was inf, right? So can't really do anything. So you have to minimize this. And we're still at stop 0. 3 is okay, so 1 goes to 3, but it's inf in the previous copy of the previous value. So you don't change anything. Alright? Okay. So let's actually get into it. So I'm going to say stop equals 0, and while stop is less than or equal to k, we want to stop after k stops. We want to say keep, well, we can do this now. We decrement stop, well actually no, we increment stop by 1 until we get to k, and then we have a previous table that is just a copy of the price table. Alright? So now what do we do? Well, we have to go for, so for each flight, in flights, right? Actually, let me see if I can, I'm going to make it from, oh, can't make it from. UVW. Do you get what those represent? The source, V is the target, W is the weight, so that's the price. We call that the price here, in this case. Okay, so we say that price of V, so we want to change the price of V. We want it to be minimized. So it's going to be itself and what? What did we talk about before? So we want to, so the target node. Okay, so like we want to change the value of the price of 1, right? But we need the way and the price of, yeah. For now, well, it's 10 to the 4. You know what? I could just make this infinity. Let's make this infinity. Just to, you know, it's infinity. Yeah, you don't know. Exactly. And you want to get the price of the city that you can go from, right? So the from city is U. You go from U to V. So you want to get the price it took to get to here and add it to the weight. So we want to get the minimum of itself and the previous price of the previous city plus how long it takes to get from that city to V. So we update it like that. Make sense, Carlos? So what happened? Exactly. And we do it from the previous table, right? I didn't do that part. But yeah, you do want to get it from the previous table and calculate it from there. Because in the previous table, we got the value from k minus 1 stop. And we want to get the answer for to k stops, right? Okay. So that's basically what we do. Now we return -1 if what? If the price of destination is what? If it's unreachable, right? So what value makes it unreachable? If that means it's unreachable. Yeah. Else just return price destination. Okay, so let's see what actually happened here. Okay, that's what's going on. All right. Yeah. So this one is shorter than the last one, isn't it? Would you say it's easier or no? Not easier? Yeah. That might have been like kind of complicated. Like why do we need a previous table? Well, that's because this is the values collected from the previous iteration, right? This was from when we had k minus 1 stops. This is k stops. So we want to actually get our evaluate from here. That's what we want to do, right? Okay. So we're good on this problem. Like it makes sense. Ricky, you have any things to say about this problem?
Maybe you said already why do you use Bellman-Ford?
Why did I use Bellman-Ford? So actually, credit where it's due. Lazaro helped me find this problem, and he's not listening right now, but he did, and this was just like iterating through itself, and the thing is that like this is the this is -1 stop, so we didn't do anything, and this is 0, right? And if we keep just doing that, then we can find that if this becomes k minus 1 and this, well, we put this here, right, and we add on to it, then like okay, so if we go from here, right, and we go through that table, right, only this is added if it's k equals 0, right? That means we don't want any stops. But in order to get to 3, we need yeah, well, 1 stop. So let's go to the next iteration, and then we can get to 3 because we evaluated for 1, right? Does that make sense, Ricky?
The graph. So Bellman-Ford is a graph algorithm.
It is, yeah.
What is the graph?
Okay, so the graph is this. Well, this is one example. Each node that goes from 0 to n minus 1. Yeah. So n minus 1, that's the biggest value for a city name, just some value. And so it's the flights, right? So we have U, V, W. U is the source, V is the target or destination, and W is the price it gets from one city U to city V. So like this. And it's directed. It's a directed graph. So basically you want to get the price from 0 to 3. So it's like a distance. It's like a distance table. You want to keep editing it with each iteration. We stop at stop equals 0, right? So we want to get, so right now where a stop is -1, so we didn't do anything. So we get the first iteration and we turn this into this, and this is the table we get when we have no stops. Because from no stops, you can get from 0 to 1, but not to anything else. But with at most one stop in between, we can get to 2 and 3. So 2 and 3's values will be changed. Does that make sense? Like why that what happened?
I know what you're saying. It makes sense, but I guess the smart solution is that this is, we can use Bellman-Ford. If k was equal to n, then we're just finding the all pair shortest path
Yeah.
in this graph.
Yeah, if k was just equal to n, yeah, you're right. Then it would just be all pair shortest path anyway. But single source. It would be a single source. So Bellman-Ford is a single source shortest path, much like Dijkstra, except so like k would be n minus 1. So it's like a thing where it has to be n minus 1, and then you do another iteration through that again to see if there's a negative cycle, negative weighted cycle, and if there is, return that there is a negative weighted cycle, and if there isn't, then you can have a table saying, okay, now we found the shortest path from source node to every node, and it's just this, right? It's just that. No, it's the number of nodes minus 1. Ricky, does that make sense?
What?
That Bellman-Ford is iterated the number of nodes minus 1. Like the whole process of doing that is repeated n minus 1 times. The nth one.
Because I think the first one is technically itself, so that's a distance of 0. You can look up the implementation, but I don't know.
I think the reason it's n minus 1 is because if there's n nodes, right? How many stops at most does it take to get back to itself? At most. Yeah. So you do it, you iterate it. Well, I think it's n minus 1 times, really, because it's just going back to itself.
Yes, that's n minus 1.
Yeah. So, and the reason I'm saying it's n minus 1 is, but if you want to check if it has negative cycles, then you have to do it n times and see if it relaxes. If it relaxes at the last iteration. Yeah, and we're relaxing it right here. This is the relaxing. No, and what I'm saying is, if you want to check if it has a negative cycle, which in that case, there's no concept of shortest path. You'd have to do it n times, and if it does relax at the last one, it means there was a negative cycle. Yeah, because that's the only way you could. So yeah, that means you kind of went through all the paths. You went through all the paths, and you shouldn't be decreasing anymore the distance through any one of them. Yeah, after n minus 1, you shouldn't be decreasing. So you do it n times and happen to decrease at the nth one.
You check it after you're done with the algorithm. So after you're done with Bellman-Ford, you can iterate again and then try to relax one more time. And if it's smaller this time, then we know we have a negative cycle.
Yeah. So like.
Yeah, you are right. And n times, but
Yeah, it's not to find the shortest spot. It is to check for a cycle. Yeah. So. Negative cycle. Yeah. So what's like the shortest path for 0 to 4, right? Oh.
So this path.
Yeah. So if it's one stop, then it's this. But if it's three stops, it's that. Yeah. So yeah, and that's kind of how the problem is kind of set up. Okay, so uh, we kind of went over two single source shortest path uh, problems. Uh, we'll go over another one. Let me see. Related to okay. I might not even do this question if it's too hard.
This would be something legal to do sacrifice.
Mm-hmm. Yeah. No, I bet working for Lead Code you get a bunch of like benefits. You know. Mm-hmm. Yeah, pretty much. You can travel among and cities. These cities are connected by flight. These flights are represented as M by M exit, not necessarily symmetrical. Called flights representing an airline from city I to city J. There's a flight I to J. Flights equals 0. Otherwise, flights equals 1. Also, flights equals I equals 0 for all I. You have K weeks. Each week has 7 days. I know, right? You have to. You can. Yeah, it is, isn't it? You can only take flights at most once per day and can only take flights on each week's Monday morning. Since flight time is so short, we do not consider the impact of flight time. For each city, you can only have restricted vacation days in different weeks, given an N by K matrix called days. Representing this relationship for value of days IJ represents the maximum days you could take a vacation in the city I in the week J. Oh my god. This is a hard problem. I don't know actually. I don't know. We may not even have time to do anything else. Not just that, but these guys are gonna have class here and they're gonna. You hate reading? I hate reading too. But reading's important. You gotta read your emails or else you make a mistake with your boss.
Well, yeah, we have to read. Doesn't mean we have to like it.
Well, you can't read? That sucks. Yeah, read the question. Let me actually just make it bigger.
You really can't read.
You zoom in.
I can't do that. Well, I already did it. I already read it out.
To travel among 10 cities to collect algorithm problems. But all work and no play makes Jack a dull boy. You can take vacations in some particular cities and weeks. Your job is to schedule the traveling to maximize the number of vacation days you can take. But there are certain rules and restrictions you need to follow. Rules and restrictions. You can only travel among n cities represented by indexes from 0 to n minus 1. Initially, you are in the city index 0 on Monday. The cities are connected by flights. The flights are represented as an nxn n by n matrix, not necessarily symmetrical, called flights, representing the airline.
Oh, you need more. Oops.
Status from the city I to the city J. If there is no flight from the city I to the city J, flights IJ equal to 0. Otherwise, flights IJ is equal to 1. Also, flights I equals 0 for all I. You totally have K weeks, parentheses each days to travel. You can only take flights at most once per day.
Yo, he was
And
Oh,
can only
sorry.
take flights on each week's Monday morning. Since flight time is so short, we do not consider.
Come on, you could remember it.
I couldn't remember it.
Do you remember it?
No.
Okay, back to flight time.
Not consider the impact of flight time.
There we go.
For each city, you
Like
only have
customers.
restricted vacation days in
Doing that
different
Excel.
weeks, given on an Annex K matrix called days representing this relationship. For the value of days, IJ represents the maximum days you can take a vacation in the city I in the week J. You can only stay in a city beyond the number of vacation days.
Dude,
Exactly.
Come on, you remember it?
I'm not even getting it anymore. Yeah, this one is listening to him trying to beat him.
I think I have COVID.
What?
I'm just kidding. Joking. All right. Do you get the
Still on the street?
yeah? It's a joke. But do you get this problem?
Dude, how could you? You couldn't even finish reading the problem.
Because you get it now. You just read it. Yeah, I know. Do you guys want to do this problem or nah? We don't have the time. We actually don't have the time. No, I'm planning on finishing this in three minutes. Because this classroom getting in. Also, I have something to take care of at my house. What? Hmm? All right, guys, do it in 3 minutes. Come on, 3 minutes to do this problem, or you lose your job or something. Wouldn't that suck?
Shut up. Of course it would. Wait, why is that even a question?
Would they make you do it? Like, once you
No,
already
bro.
have a job, you had to, like, do, interim,
Yeah, like every
interviews.
3 months.
Every
Imagine,
3 months
bro.
You have to go back and do another one of these.
Dude,
Like,
I would die. I would just die, bro. If I had to keep doing this every 3 weeks during the internship, I would die.
No, I'm saying once you're hired.
Let me see example.
Bro, actually, if that was like an internship, I like it. So like after the internship, I'd be ready to interview again.
Yeah, but I wouldn't practice on like working. I'd practice on leetcode.
Yeah.
Doing work.
Oh, okay, you got flights and days.
What if like in a job, you have to do it every 3 months or so, but you're actually competing against new hires as well.
That's true. I think that if you can do your job, you can center your div and work on your SQL, you're good. Like it's fine.
Wait, what does days represent again?
I forgot what was days.
Days
Days.
you can take as vacation, but
Days
I don't know
represents
what
the
the
relation.
problem is. Like, what's up?
score them.
I don't know, bro. I don't know what the hell you're. Sorry, what you're supposed to do.
I fucking hate you.
I wish I could just have a 3-day weekend every day of my life.
Yeah.
That would be nice. No, I mean like after I graduate.
It was like this whole thing of wanting to start this 4-day work week.
Yeah, but with increased hours during the day. Marginally though. Maybe 2 hours. But then again, you get the whole weekend. It pays off. It pays for the missed day. Like if you can do a 4-day weekday, but you add 2 more additional mandatory hours, you make up for it, right?
Yeah, it is making up.
You scroll up again.
The 8-hour day, you split that. Yeah, this is making up for it.
Mm-hmm.
Can I say example two?
For a whole 3 weeks.
You know how many weeks is the size of flights?
Uh,
Just some notes.
I don't know. I have no
This
idea.
is- Oh, there's N city.
There are no
And
flights.
you stay in H city 1 week. So,
Oh,
yeah.
okay. So this is has no days. I is the city that you're in, and J is the amount of vacation days.
Yeah.
Of that.
Mhm.
Since you have zero flights, you stuck at the city, so then you only have the 1 day a week. Wait, so you have 3 weeks total?
Yeah.
Oh, okay.
Wait, so you could be at some cities that you can't travel to other cities.
Yeah.
And you
Yeah.
can be stuck at just one city.
Yeah, and if you're in one city, and you can also just stay in that one city. You don't have to necessarily move. Because you're trying to minimize the number of days you work, you're trying to maximize the number of days you vacation, which is
That's-
given from the days already.
That's tease. Look at that. 777. You can't actually go anywhere. So you're stuck over only having one.
Mhm.
Days or like for each city, how many days you can play per week?
Per week, yeah, per week.
Yeah.
So the 777 meant that if you went to another city, you would have had the full week of vacation, but there were no flights. So
I know.
stuck there.
What a terrible situation.
Oh my gosh, just don't do any work at all. For example, 3.
Mhm.
I think it's Dijkstra, but now it's just keeping like the lowest wage. You want the lowest work days and highest vacation days.
I feel like that's exactly the previous problem with this bid.
You think it's Bellman-Ford? But why? You're visiting all of it. That's the same thing as single source.
But you have a limited number of weeks, right?
Do you?
Yeah, you only have 3 weeks to work out.
Yeah.
Oh, you only have 2 weeks?
Yeah, you only have
The
3
amount
weeks.
of weeks we have is the amount of cities there are now. Wait, it's only 3 weeks?
Only
It's
3
always
weeks.
3?
Always 3.
Can you go up?
Yeah, it's always 3.
Always 3.
So a week.
You slow
Week.
it down to constraints, please. Yeah, it says K weeks. Yeah, it's
Yeah,
not.
so it is K weeks.
It's not always 3.
But you could like think of it like K, like the K different stubs.
Yeah.
Like the weeks that is different stubs. You'll make 3 different stubs in there.
But K is going to be equal to.
Instead of the price of the flight, it's just the number of days you get for vacation.
But K is equal to N. Is it not?
Yeah.
Oh yeah, and
Wait, K can be equal to N, then it's just
And
Like
is
how much
K
is that?
is N.
Yeah.
K
K
is
is
N.
always N.
Yeah.
Yeah.
All right, guys. I'm gonna.
Actually, wait, no. No. K is not.
I'm gonna end the stream. We're gonna figure this out on our own. So, yeah. Thank you all for attending.